Hi everyone, and welcome to another session, the last session for graph problems. We will be solving now a maximum independent set problem. You know that this is an NP-hard problem. We have already seen the theory of that in the previous session. Um, we know what a maximum independent set problem is, and we will be using the help of this .py. We will do it in this Jupyter notebook, but the .py document you will have it already already coded. This has been developed by Rafael Martin Cuevas. He's another teacher, another professor of these masters. You probably already know him. And yeah, public thank you for him for developing this. So these are some auxiliary methods that we will use in our development on the maximum independent set. Um, here we have three functions. Please remember to install the requirements txt. The first one is building the graph. So we will have an adjacency matrix. You will see afterwards what this is. But it's basically a list of lists where we have zeros and ones, and you have uh, all the matrix for the connections between the nodes. I can give you an example. It would be something like this. For example, 0, 0, 1, 0, 0, 0, and 0, 1, 0. Sorry here. So it would be something like this, but bigger. Where we are saying, okay, so node 0 we have a 1 here, so we will only have an interconnection between node 0 and node 2. That is this position, and an interconnection between node 2 and node 1. This is the matrix that we will be talking about, but it will be bigger because it will be representing our problem afterwards. So we will have something similar like that. Then what we define is with NumPy we convert the kind of object that we are using here. We get the length of that object, and we range we range that to see what are the number of nodes that we have. If you remember that adjacency matrix that I did, it had, sorry, let's have it again here. The length of this is a list of lists, so the length will be 1, 2, 3. It will have position 0, position 1, position 2. That would be the nodes that we have. Node 1, 0, node 1, node 2. So this is what we are doing here. We are getting the length. So for that, we will get the number of nodes. And then we arrange it to have the list of nodes. Then we see where do we have a 1 in this matrix. And with that, we will have the rows and the columns because we will have the position of those ones. In this case, it would be 0, 2. In this case, it would be 2, 1. Okay. And then we get the edges with these ones because only in the ones we will have an edge between the nodes. So we make a list and with all those edges, the positions of those edges. And then for the network X graph, we just use the library that we talked before, network X. We build the graph and then we add the nodes and the edges and we return this object. Here with this object afterwards, what we will do is just build the path, the edges in the path, and we will draw it. This will be our solution. So we have the path will be the, the real solution. In the graph, remember the graph has so many edges, and you may only select some of them. So this selection will be the path. Here we will have the general graph with all the edges, all the nodes, but the nodes and the edges with these color that are the ones in the path will be the solution, like the ones that were in blue in the slide, against the ones that were in white. And then we just make the width of the selected edges a bit wider. And then with this, the only thing is that we build it from scratch again from the adjacency matrix. And that's it. I will delete this here. We will start building the graph in the Jupyter notebook. So for building the graph, we'll have this here. Please remember to import everything here. We're connected to the kernel. Okay, running this. Okay, and we imported the aux functions, so the .py, that this one. So with the graph, let's build the graph. So this here will have 1, 2, 3, let's say 4, 5, 6, and 7, right? So 1, 2, 3, 4, 5, 6, 7. And we will put one here, one here, one here. One, 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 another one here, another one here. I'm just building the graph, so selecting which of the edges will be painted. So which will be the connections between the nodes that we will be painting here. We'll have here 7 nodes. It will be a graph with 7 nodes. Why do I know this? Because of the thing that we saw in the when getting the length of the number of nodes. We'll have 1, 2, 3, 4, 5, 6, 7 entries of this list. So those are the number of nodes, and then we'll have, for example, here this is an edge between the 0 node and the 1, 2, the 0, 1, 2, 3, and the third node. There will be an edge between the node number 0 and the node number 3. So this is how we are building the graph. This is the matrix. So now we go for network. We will build the network X graph. We will build this object that we will get from the auxiliary functions that we had dot build network X graph, including the graph. Let's draw it. Auxiliary functions dot draw graph because we have the network X object. So yeah. So this is this is our graph. As you can see, we said before, okay, we'll have a connection between the 0 and then node number 3. We don't have any more connections between the 0 and anything. So 0 and number 3, and there it is. Please remember that if I run this again, it will have the same graph but with another form, because this is random. So you may have, as you know, I run it again because I write some explanations here. So please remember that you may have in the Jupyter that I uploaded to materials, you may have a different version of this graph, but it will be the same one with the same connections between the same nodes. Now what we can do is run the problem in a simulator. So find the maximum independent set in this graph. For that, we will be doing the same sampler equal simulated annealing sampler nodes equal, and here we will use the wave network x dot maximum independent set, and then network. What are the arguments here? We have the graph. I get the mistake over and over when writing this. We'll get this sampler equals the sampler that we already did, and let's make these 2.0 this other variable. You can try to change this and see how this evolves, but let's try it with 2.0. I think it's a good value. So let's print what we will get here, these nodes. These are the nodes that are the solution. So which nodes are we selecting here for the maximum independent set? And these are 0, 1, and 5. So let's visualize these with a function that we got before, auxiliary functions draw from network X, because we have a network X graph, and we have path equal nodes because we already have the solution, and it is this list. Okay, so this will be our solution. As you can see, there is no connection between any of these ones, and this is the maximum combination, the maximum number of nodes that we can make without being interconnected between them, because we cannot add anything else. This is the best combination possible. So yeah, as you can see, these may vary on the when you have a graph, you may have several solutions for the same graph, rotations and everything, but even solutions that are not rotations in themselves, but may vary, but have the same number of selected nodes. So yeah. This is an example. This is a really simple example. As you grow the graph, as you grow the possibilities, the number of interconnections, this becomes a really dense problem that is a really good case for getting to know the advantages of quantum computing. So I hope that this has been helpful for everyone. Thank you for watching until here. And please, if you have any questions, doubts, whatever, please feel free to reach me, and we can try to solve them. So yeah, thank you everyone.